Welcome everyone. Today we will explore a classic yet powerful dynamic programming problem, the gold mine problem. Join me as we journey through the mines of logic, discovering how we can unearth the maximum gold through optimal paths. Imagine a miner standing at the edge of a vast underground mine, a grid full of golden opportunities. Each cell in this grid represents a specific amount of gold. The miner can begin from any row in the first column, but his path is constrained. He can move on the right up, or right down. Our task is to determine the maximum amount of gold he can collect by the time he reaches the end. Let's understand the problem more vividly through examples. In the first example, we see a clear optimal path starting from the second row, then dipping down and moving right, collecting a total of 12 gold. In the second example, there are multiple paths, each yielding the same maximum, which is 16 gold. This underlines the fact that the solution isn't always unique, but it's always optimal. Before diving into the code, let's look at the rules of the game. The grid can be up to 500 rows and 500 columns, which means we must avoid brute force approaches. Our algorithm should be efficient with a time complexity of n times m, and with clever design we can even optimize space to constant auxiliary usage. Let's start building the solution. We determine the number of rows and columns and initialize a dynamic programming table that is a 2D vector dp, where dp ij will represent the maximum gold collectible starting at cell ij. The main strategy begins from the last column, moving leftwards. This backward approach ensures that every decision we make at cell ij is backed by already computed optimal choices from the next step. From each cell, the miner considers three possibilities: move directly to the right, move diagonally to the upper right cell, or drop diagonally to the lower right cell. We carefully handle boundaries to avoid stepping outside the grid. With the options evaluated, we now pick the best one. We update the current cell in the DP table as the value of gold at the current cell plus the maximum gold collectible from the three potential next moves. Once we have filled the DP table, we scan the first column where the miner could have started from and return the highest value. That value represents the maximum gold the miner can gather starting from any row in column 0. To summarize, we approach the problem with a bottom-up dynamic programming strategy, ensuring optimal substructure and overlapping subproblems were efficiently handled. The solution is elegant, fast, and applicable not just to this problem, but to a range of real-world scenarios, from pathfinding in AI to decision-making in games and even strategic resource planning.